Hello everyone, welcome to our channel. This is Dinesh Imye, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In this session, we will understand the filters and regulators. There are different types of filters available. We shall consider the capacitor filter for our discussion. Here you can see the circuit diagram for a full wave rectifier with capacitor filter. This forms the bridge circuit. In the previous session, we had seen a circuit where the bridge arrangement was looking different than this. This is also considered to be bridge arrangement. So D1, D2, D3, D4 forms the bridge circuit, and we supply AC signal for this. And here we will be getting the pulsating DC output after this particular point. And the pulsating DC will be fed as input to this capacitor. So this capacitor C will be working as the filter circuit, which is connected across this load resistance RL. In fact, we can interchange the positions because these two are connected in shunt paths. And now here you can see the pulsating DC, which is fed as input for the filtering circuit. Now when there is a pulsating DC coming in, what happens with the capacitor is, we know one of the properties of the capacitors is charging and discharging, and that is how the capacitor will be working as a filter in this circuit. Now let us get into the waveforms to understand this operation well. Now let us say the pulsating DC, which looks like here white in color, and this will be supplied to capacitor to charge the capacitor. And capacitor, let us say it starts charging to its peak. Initially, of course, we will be having in the initial cycle right from 0. So the capacitor charges to its peak, and once it charges to its peak, it starts discharging. So discharging happens like this. So slowly the capacitor starts discharging. Then once again, when there is a pulsating signal comes in, the capacitor again starts charging. So it starts from this particular point and it reaches to its peak. Then again it starts discharging like this. So if you look at this particular thing, this segment, so what we can see here is, earlier with the rectifier, the peak to peak variation was from 0 to the peak output voltage. But now with the help of capacitor, we have reduced the peak to peak voltage. Ignoring the first cycle, what we have is the peak to peak voltage, now it has been reduced to this limit. So this is V gamma peak to peak. So this is going to be considered as the output of the filter circuit. So rectifiers has the output which has huge variation in its output, whereas employing capacitor will bring down this variation. So we say the ripple, the variations in the output has been reduced. So this we are doing in attempt of getting a DC output which is a straight line. So with the help of the capacitor, the variation has been reduced. Now how do we decide the value of the capacitor? The value of the capacitor C is given by IL. So where IL is the load current and T1 divided by V gamma. So C is the capacitor, IL is the load current that is charging the capacitor, T1 is the discharging period. So from this point to this particular point. So this time duration will considered as T1. So capacitor C is given by IL into T1 divided by V gamma. So where V gamma is the peak to peak voltage. So this is how we can reduce the ripple content from the rectified output using a capacitor filter. Now further the ripple can be reduced by employing another capacitor across the same path. So as many number of capacitors we have, so filtering happens smoothly. So we'll be getting less ripple, less variations we'll be having in the output voltage. So this is all about the operation of capacitor filter. Now let us understand the regulators. Zener diodes are the main component used in regulator circuit. So let us understand the Zener diode before getting into the concept of Zener used as a regulator. Now the Zener diode is represented like this. This is the symbol of Zener diode. This is said to be anode and this is said to be cathode. So Zener diode will be employed in the reverse biased mode in the regulator circuits. So let us understand the reverse characteristics of the Zener diode. So the reverse characteristics of Zener diode look similar to the reverse characteristics of any PN junction diode. So let us draw the reverse characteristics of the diode. So this is the third quadrant what we have, and the x-axis represents the voltage. So this is reverse voltage, and the y-axis represents the current in milliamperes, and this represents the reverse current IR. So the reverse characteristics of a Zener diode looks like this. So as it was with the PN junction diode, so here too there will be a small, very small leakage current that flows in the reverse bias mode. And here we have a couple of parameters which are important with respect to Zener diode to be noted. So what are these? Very first one, the first parameter is Zener breakdown, which is represented as Vz. The very first parameter is Zener breakdown, which is represented as Vz. So Zener breakdown is the reverse voltage at which the Zener diode enters the breakdown region. So in this diagram, this point is the Vz point. So minus 6 volts is the Zener voltage, Zener breakdown voltage. So when the diode enters this breakdown region, there will be a constant voltage maintained across the diode, what we call as Zener voltage. And the second parameter is minimum Zener current. Minimum Zener current, which is represented as IZK. Now coming to this graph, IZK is the reverse current that is read at the knee of the reverse characteristics. So at this particular point, what is the current? So that shall be read as IZK. So IZK is the reverse current read at the knee of the reverse characteristics of the Zener, and this is the minimum current that is required to maintain the breakdown region. If you go less than this, then Zener will not be working in the Zener breakdown region. So we should make sure that the circuit elements will allow a minimum current of IZK at least, so that the Zener will be working in the breakdown region. And the third parameter is maximum Zener current. This is represented as IZM. So this is the reverse current again, that the Zener can carry maximum without destroying, or this is the maximum current in the reverse direction what the Zener diode can carry without exceeding the maximum dissipation, maximum power dissipation. So usually this is the level minus 40 milliamperes is the point, so what we consider as IZM. Right, and the fourth parameter is maximum power dissipation. Maximum power dissipation, and we represent this as PD, maximum power dissipation. So this is the maximum power what the Zener diode can handle without destruction. So this is called as maximum power dissipation, and this parameter PD is given by Vz into IZM, whereas Vz is the Zener breakdown voltage or the Zener voltage, and IZM is the maximum Zener current. So these are the parameters associated with any Zener diode. Now keeping these parameters in mind, we'll use any Zener diode to work as a regulator. So now let us understand how a Zener diode can be used as a regulator. So here we have two conditions. Condition number one is when there is load connected, and condition number two is when there is no load connected. So Zener diode will be analyzed as a voltage regulator under two conditions. One is no load condition and second one is loaded condition. So we'll understand these two conditions and see what are the differences between these two. So let us get into Zener diode as voltage regulator in two different conditions, that is as mentioned, with load and without load. So first let us consider without load condition. Let us say like there is a voltage source . Let us call this as ES, and let us consider a Zener diode across this. And here we have a series resistance, and let us say this is RS, and here we have a Zener diode. Connected like this. So make sure that the Zener diode is connected in reverse bias mode. Let us say this is anode and this is cathode. And let current IS be the input current that is flowing in the circuit, and here we have a voltage across the Zener, what we call as Vz. And let us apply KVL, Kirchhoff's voltage law, through this path, so that ES is equal to IS into RS minus Vz. So RS is equal to ES minus Vz divided by IS. Now because this is the only current that is flowing through the circuit through the Zener diode, this can also be represented as IZ. So this equation can also be written as ES minus VZ divided by IZ, or this equation can also be written as IZ is equal to ES minus VZ divided by RS. Now the point to be noted here is the series resistance RS should be selected in such a way that the IZ, the current IZ will not go lesser than IZK, that is minimum Zener current, and will not be higher than, at the same time will not be higher than the maximum Zener current IZM. So the RS value should be selected in such a way that IZK should be less than IZ and IZ should be less than IZM. So this is the design constraint we have in this particular circuit. Now coming to the Zener diode as voltage regulator with loaded condition. So let us look into the circuit diagram for this. So let this be RS, and here we have a Zener diode connected. So this is ES, this is RS, and here comes the circuit current IS. Now we need to consider a load, so let us connect a load across the Zener. So let us say this is RL. Now look at this. So IS is the input current that is flowing through the circuit, and when it comes to this particular node, it will be splitted into two currents. One shall be called as IZ, the other shall be called as IL. So the current that is flowing through Zener shall be called as Zener current IZ. The current that is flowing through load resistance shall be called as load current IL. Right? And here we have the output voltage V0, or this can also be called as VZ. So now IS can be written as IZ plus IL, right? And VZ just like this. So by applying KVL, we can write the expression for the value if I want to determine what is IZ, or if I want to determine VZ, or if I want to determine IL. So we can apply KVL and find out the values. So from the circuit we can write IS is equal to IZ plus IL. Let us call this as equation 1, and IS can also be written using KVL. IS can also be written as ES minus VZ divided by the series resistance RS. Let this be equation 2. By equating these two equations, I can write IZ plus IL is equal to ES minus VZ divided by RS. And we know that here this is the input current which should be limited by the maximum Zener current. right? So I can also write Is is equal to Izm. So Izm can also be written as Iz plus IL. So now this is the maximum current that should be allowed through the circuit, so which can be controlled by using the resistance Rs. And if this is the maximum current and which is written as Iz plus IL, so considering this Iz and IL that is flowing through Zener and RL. So let us say, like for example, if the load gets maximum current, considering if RL is minimum, load will be getting the maximum current, then Zener will be getting the minimum current. Then Izm can be written as Iz min plus IL max. Izm can be written as Iz min plus IL max. So in this condition, this Iz min should not be less than Izk. So that is the design point what we have. So this Iz min should not be less than Izk. And the other case is Izm can also be written as Iz max plus IL min. So if the load current is going to be minimum, so when the load current is going to be minimum, if RL value is selected as maximum value allowed, then the load current is going to be minimum. If it is too high, then IL min is going to be 0, then all the current will be flowing through Zener, that is Iz max, and this Iz max should not be more than this Izm. If not, the diode is going to be blown off. So this is the design constraint what we have. So we have a load resistance RL using which the Zener current can be controlled. The current that is allowed to pass through the Zener diode can be controlled. So this is the working of a Zener diode as a voltage regulator under no load condition and under loaded condition. So in this session we have understood the operation of capacitor filter and the regulator, where we used Zener diode as the regulator, and that's all what we have for this session. Thank you.